I'm going to continue with presenting the basic features of this cohomology theory. The first one was semi-continuity, which is very nice, and it will be very useful. And now we will see a first relation with the usual cohomology. So we will move slowly towards relations with the usual cohomology. And that's, so I think that's the second. I'm going to speak about the kernel bundles. That approach is due to Lazarsfeld. And this was one thing that completely killed the, I mean, people working in Brilliant theory were used to apply the base point free pencil trick. And this technique using kernel bundles completely killed this principle. And what's all about? So we have X, again, a projective variety over complex numbers. L, this time we need to take it globally generated. And now we just look at the evaluation map. And we take the kernel, which we denote by ML. That's the notation introduced by Lazarsfeld. And it's a vector bundle of rank, the dimension of the linear system, and whose determinant is L inverse. Okay, that's now what we can do is just to take exterior products. And then we will have again a short exact sequence, wedge p plus 1, ml, wedge p plus 1. Let me call, no, I will stick to this notation, to OX. And the co-kernel will be wedge P ml tensor L goes to 0. And we can, so we have this, short exact sequence of vector bundles. Now we can twist by LQ minus 1. By LQ minus 1, and then take global sections. And what we get is the following. 0 goes to H naught wedge P plus 1 ML tensor LQ minus 1 wedge P plus 1 H naught L. And now we took global sections. So this is H naught L Q minus 1 goes to H naught wedge P ML tensor L Q. It will continue with H1s, and the result proved by Lazarsfeld, is that if we just look at this, the co-kernel of this map, that's just Koszul cohomology. So KPQ XL is isomorphic to the co-kernel of, let me call this alpha just to be shorter, which is of course isomorphic to the kernel of what's coming next. So we will have H1 wedge P plus 1 ML tensor L Q minus 1 to wedge P plus 1 H naught of L tensor H1 L Q minus 1. Sorry, oops. So if by any chance this H1 is 0, then the Koszul cohomology space will be just an H1, which is nice. We like this. The difficulty here would be just that we don't really understand. I mean, if, for example, we want to make some Koszul cohomology groups vanish, then we will need some vanishing for this group, which will come from the positivity, some positivity properties of these bundles. But this is not completely understood. Which kind of positivity is it realized? Although this is this looks pretty simple because we just have the Euler sequence on the projective space. We pull it back on X. It's as simple as that. This is omega 1 of 1 on the projective space pulled back on X. But still, dealing with it, it could be very tricky. However, that's a more geometric description, and this can be taken for definition for Koszul cohomology. It's a more geometric description. Before we saw that Koszul cohomology is an algebraic object. Now it becomes more geometric. Okay, and let's, of course, we can play the same game. If we compute in general KPQ of X, F, L, V, F is a coherent sheaf, we have to plug it here, 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 everywhere, this F. And again, if we consider V just a vector space that generates L, we will get a similar description. So these things are just variations on the same thing. Okay, let's just for fun, let's compute the Koszul cohomology of P1 in P3. So we know that if we P1 in P3, the rational normal cubic in P3 has the ideal generated by three quadrics, and these three quadrics have two relations between them. But let's just recover this this fact by using the description of Lazarsfeld. So, for example, of course, KP0 will be all 0 except for K00, which is one-dimensional. That's just for from the description. And now let's go to, for example, K11. K11 keeps track of the generators of the keeps track of the quadrics in the ideal of the curve. So by this description, this will be the kernel of the map from let's see, H1, wedge 2, let me call L to be OP1 of 3, ML 2. Here we would have H1 of P1, which is 0. So this is nothing. It's just H1 of wedge 2 ML. And now, what's the dimension of this guy? So H0, just remark that H0, wedge 2 of ML, is isomorphic to K20, just by the definition. So K20, here we would have 0, so there is nothing coming from here. So it would be just K20, the co-kernel of this map. So this was 0. And now just apply Riemann-Roch. So H1, H0, wedge 2 ML, minus H1, wedge 2 ML, is just by the Riemann-Roch, the degree of this one, wedge 2 ML, plus what's the rank? So the rank is the dimension of the linear system, which is 3. Now we take wedge 2 of this one, so it's 3, choose 2. This is 3. So the rank is 3 times 1 minus g is 1. And now if we compute the degree of this one, we find it what is it? Let's see. The degree is minus 6. So it's minus 6 plus 3, which is minus 3. Right? Because is, we know the degree of ML is minus 3, and this is 2 times minus 3. It's just a formula computing the degree of wedge products. So this is minus 3. And this was 0. So H1 was 3. So actually K11 is 3-dimensional. Right? Now if we go to K21, sorry. So this should keep track of the relations between the quadrics in the ideal. So K21 this time will be H1 wedge 3 of ML. That's just the determinant. This is wedge 3 is the determinant, so this is H1 of OP1 of minus 3, which is, this is 2-dimensional. It's isomorphic to H0 of 1 is 2-dimensional. So we have 3 quadrics and 2 relations between them. Right? And now if we just compute K12, for example, we find it 0 and so on. We just apply Riemann-Roch several times, as many times as we want. And here in the computation of K12, we will need this to know this space, which was 2-dimensional. So it's really something very, it's very geometric. And now let's go to some other properties of so just remember that this the use of the kernel bundles was one geometric way of computing Koszul cohomology and hence computing minimal resolutions. There is another way, which I'm going to discuss tomorrow, which is by means of Hilbert schemes. This was a completely new view introduced by Claire Vazin in relation with Green's conjecture. Okay, now let's go to basic results. And they all are inspired by the usual cohomology, similar results in usual cohomology. The first one would be hyperplane section theorem. So let's suppose L globally generated on X and D in L connected divisor. Then, of course, we have let's just assume that that's not the projective line, which is a kind of trivial. We have this restriction map of L to D. And we also have restrictions of sections. So this restriction map will induce a restriction from H0 L tensor OX to H0 LD tensor OD. Okay, and this will induce furthermore a map between ML and ML restricted to D. Okay, and then just analyzing this situation and taking wedge products, we will have some restriction map, and using this theorem of Lazarsfeld, which I'm not going to erase right now. Okay. And we will get an induced restriction map from KPQ XL to KPQ D L restricted to D. And the result proved by Green, which he called Lefschetz hyperplane section theorem, is that if H1 of OX is 0, then the restriction map induced at the first level, so for Q equals 1, KP1 XL to KP1 the L restricted to D, is an isomorphism. And if H1 L to any positive power is 0, then the same is true for any KPQ. And the same. And restrictions are isomorphisms for all P and Q. So this applies, for example, for regular surfaces, like rational surfaces, K3 surfaces. But it doesn't apply for abelian surfaces, for example. There is a bunch of varieties that are left out. And we will see when we discuss Green's conjecture, we will see why that's one of the reasons Voisin chose K3 surfaces for testing this conjecture. It's not the only one, but it's one of the reasons. Okay. I'm not going to prove this. It's just it can be found. A proof can be found in Green's original paper. Okay. Another. So we had restriction maps, like for usual cohomology. We have duality, like Serre's duality, and this comes actually from Serre's duality. Here we have another result, which is again due to Green. So L is globally generated on X, which is smooth this time, of dimension n. We put R is the dimension of the linear system, and assume now we have a set of vanishing conditions which are imposed, HI LQ minus I hi q minus I plus 1 are all 0 for I from 1 to n minus 1. So these are automatic if L is, for example, sufficiently positive. So if L was very positive, then these conditions are automatically realized. And we just take KPQ, XL. Well, the dual of this one is isomorphic to K R minus N minus P N plus 1 minus Q. X, Kx, and L. So Kx here stands for that coherent sheaf F. So we have to we have a perturbation of the. Okay, so again, I'm not going to prove this. Just a remark that for curves, if n equals 1, then these conditions are superfluous. There is no condition. For n, we have no condition, no vanishing condition. And it's actually very simple for curves, because we just apply this description. I mean, if we just have a look at KPQ, X, L, and we dualize it, is the co-kernel of that map alpha dualized, which is now we can see this as the kernel of the dual maps when we dualize this one. So is this H0 wedge, let's see, PML tensor LQ dual to wedge P plus 1 H naught L dual tensor H naught LQ minus 1 dual. And now we apply Serre's duality here. So by Serre duality, this is just the kernel of the map from H1. We have wedge P ML dual tensor K X tensor L minus Q to H1. Wedge P plus 1 H naught L dual tensor H naught Kx tensor L1 minus Q. And now just observe that wedge P of ML dual was isomorphic to wedge R. So R is the rank of ML tensor L. Right? Because we have the R minus P, sorry. We have the pairing from wedge R minus P ML dual tensor wedge P ML dual to L, which is a perfect pairing giving this this isomorphism. So we just can't replace. And H naught, likewise, wedge P plus 1 H naught L dual is isomorphic to, let's see, this is R plus 1 dimensional. So this is wedge R minus P H naught L. Right? So we just yes, we just replace here everything, and we get, this is the kernel of the map from H1. This is wedge R minus P ML tensor Kx tensor L 1 minus Q goes to wedge R minus P H naught L tensor H let's see. There's something wrong here. H1. Okay. H1 kx tensor L1 minus q. Okay, good. So this is just by the theorem. This is just k. And let's see. This is r minus p minus 1. And then we have minus q, if I'm not wrong, x kx L. So n was 1. Sorry, no, this is 2 minus q. I'm sorry, 2 minus q. So for n equals 1, we get exactly the same thing. So that's a proof for curves. And somehow the most interesting case is that if L itself is kx, supposing that kx was globally generated, so the most interesting case occurs for L equals kx if this was globally generated. And then we will just have kpq x kx dual is isomorphic to k r minus n minus p. Then we will simply have n minus q x kx. Because if we repeat this, it will just shift the degree here by 1. So we have a pure duality between these Koszul cohomology spaces. And it's interesting to see what happens for curves. So for curves, if we look at the Betti table, this result just gives translates into a symmetry result for the Betti table. So for curves, this gives symmetry of the Betti table, which is the Betti table will look like, so we will have 1 here, then we will have something, so some dimensions. So we have 1, again some dimensions, then we have zeros, and this is g minus 1, the column g minus 1, that's a column 0. So the Betti table is symmetric with respect to its center. So if we choose the center here, the dimensions will be the same. That's what should be like this. There is nothing here. Okay, this could go up to here if the curve is hyperelliptic. So that's particularly a nice feature for canonical curves coming out of duality. And of course, we have a version with some vector bundle plugged here, E. Then we will have E dual tensor K with some suitable vanishing relations. I don't want to insist. So we have a version with some V and also with some E and also with some V which generates L. Okay, now we have another result, which is a comparison to the usual cohomology. So here we have the following result. So again, X is smooth connected projective, L globally generated, F a coherent sheaf on X. And we assume that the following vanishing conditions are realized: HQ minus I F tensor Li equals 0. This happens for I from 1 to Q minus 1. So again, these conditions are automatic if L is sufficiently positive. HQ minus I F tensor Li plus 1. Observe that they are somehow similar to the conditions needed in the duality theorem. This is 0 for I from 0 to Q minus 1. Then HQ of F will be isomorphic to K R minus Q plus 1 X F L, where R is just H naught L minus 1. So we can actually recover the usual cohomology of any coherent sheaf from this twisted Koszul cohomology with values in some sufficiently positive bundle. So, for example, what gives for F is OX, X is a curve, then we will get H1 of OX is isomorphic to K R minus 1 to XL if, and these conditions are just, they reduce to the condition that L is non-special. So, in other words, the genus of a curve can be read off Koszul cohomology of that curve with values in any non-special line bundle. Okay. Now, that's not very surprising because we saw that Koszul cohomology can be computed from the usual cohomology by Lazarsfeld's result. So it was somehow logical that we could also go the other way around. Now we have Castelnuovo-Mumford regularity, which has also something to do with Koszul cohomology, and this actually comes from it can be seen as a consequence of this relation. So let me just remind you the definition. So if L is very ample, or even globally generated and ample, that's enough on X, and F is coherent, then we say that F is M regular with respect to L if Hi of L tensor Lm minus I is 0 for any I bigger than or equal to 1. And the regularity of F is just the minimal M that realizes. So it's the minimum M. Okay, and the following result, which was first proved by Green, shows that this regularity has something to do with the size of the Betti table. So specifically, the result is the following. The regularity of F is the minimum M such that Kp m plus 1 x f L equals 0 for any p. Right? So if I mean, the regularity is exactly the row where the Betti table stops. So when we find all zeros on a whole row, then this will be the regularity. So what's beyond that row would also be 0. So if we find only zeros on a row, this will be the regularity, and everything under will also be 0. Okay. So just let me state a corollary, an immediate corollary of this theorem. So if X is a curve and L is globally generated on C, again this is the case where it's just globally generated and ample. So that's non-trivial. So again, it makes sense to talk about regularity also in this case. Then we will have H1 of L is 0, so L is non-special, if and only if KPQ on X. KPQ X, L is 0 for any P and any Q bigger than or equal to 3. This is just a definition of regularity. This would mean, being non-special means that is too regular. And it's basically the same.
Green's theorem is true for L globally generated.
The theorem, I don't know if the regularity is if this definition of regularity works well for just globally generated. And when we speak about regularity, we ask at least to be ample. But if we just make the definition, the regularity to be this one, then definitely it's true, because we just have to apply this result. But in general, if we want to work with regularity, we need to have it at least ample. Okay, and so we saw that there are many features shared by Koszul cohomology and usual cohomology. And well, when we talk about usual cohomology, there are two things we wish to settle, which is vanishing and non-vanishing. We would like to know whether some cohomology is 0 or not. And that's also the case for Koszul cohomology, and this is maybe the main issue in the whole theory, to settle vanishing or non-vanishing. In other words, before going further and compute completely some Betty table, we would like to know what is the distribution of the zeros in that Betty table. Okay, and there are some vanishing results, which I'm just going to code without proof. When do I have to stop? 5 minutes to 4?
5 minutes, 10 minutes, 5.
Okay. Yeah, okay. Yeah. And probably I should. Okay, let me start with the vanishing. There are some general vanishing results, which is one is for the projective space, and this is sharp for projective spaces. So if W is in H0 of P R, OPR of D is of codimension C, then KPQ PR O of K, O of D, and W is 0 if K plus Q minus 1 D is at least P plus C. So we have some numerical conditions ensuring that this thing is 0. I'm not going to prove it. Just let me mention that the proof relies on regularity of kernel bundles. Yes. So basically, the idea is that if we take the kernel bundle for this one on the projective space, then the kernel will be one regular, and then when we take wedge products, which were used in the definition by Lazarsfeld, were used in the definition of Koszul cohomology, these wedge products will be regular. So wedge P of the kernel bundle will be P regular because simply this is we work over complex numbers, remember? So wedge P is a direct summand of the tensor product. And if we have two sheaves, one of which is M regular, the other one is N regular, then the tensor product will be M plus N regular. So the proof basically relies on regularity. So, and the description due to Lazarsfeld. So you have to make some cohomology vanish. And this is precisely what's, what comes out from Lazarsfeld's description. Okay, and there are some other general vanishing results. I'm not, I think I'll skip them. I'll just go to non-vanishing part, which is for non-vanishing, the best result we know so far is due to Green and Lazarsfeld. We can extend it a little bit. I mean, Green Lazarsfeld worked in the following context. So if X is smooth and L, this time not necessarily globally generated, just any bundle, and suppose that L can be decomposed like L1 tensor L2. Of course we can, I mean there are plenty of decompositions. I mean, any L1 you choose, you'll automatically find an L2, but here we impose that each of these Li's have at least two sections. And then this Koszul cohomology space is non-zero. So what they do actually is they are able to produce out of this decomposition to produce non-zero Koszul cohomology classes. And we can extend a little bit this construction. Well, the idea is the same. So we just consider X as before, smooth, projective, complex, and so on. E a rank 2 bundle on X. In the case of Green-Lazarsfeld, E is just the direct sum of L1 and L2. It's a special case. And we take L to be the determinant of E and V to be H0 of L. Okay, and now we have a determinant map which goes from wedge to H0 of E to H0 of L, which we denoted by V. That's the determinant map. Okay, we choose T to be a global section of E. Then we have an induced map which we call dt. That's linear this time. So any section S will be mapped to D S wedge T. Okay. And we choose now U, a vector space of sections such that it's transverse to the kernel of dt. Then dt restricted to U will be injective. Let's call W the image, which is isomorphic to U. Okay. Then we can construct a Koszul class out of this data, which is the following. So we just look at D from wedge 2 of U to V, right? That's linear. So then this D can be seen as an element in wedge 2U dual tensor V. But this is just isomorphic to wedge 2V dual tensor V. And if we just put the dimension of U to be P plus 2, this is moreover isomorphic to wedge P of W tensor V, which is included in wedge P of V tensor V. And now we have a little lemma which is due to Vazin, which says that this element here is actually a cocycle. If we apply the Koszul map to this one, we will get 0. So this element gives a class in KP1 X and L, right? We don't know whether it's 0 or not as a class, but we know that it's a class. I mean, it just suffices to apply the Koszul differential and see that it's 0. That's the content of this lemma. Okay, and what's now the how does it work in the case of Green and Lazarsfeld? So just for simplicity, for GL, just assume that both L1 and L2 are globally generated. Well, if they are not, then there is some extra work to do, but basically the idea is the same. So if they were globally generated, then we can find two sections, S1 and S2, such that the zeros intersect in something of codimension at least 2. Okay, and now we can take E to be L1 plus L2. Take T, this pair. And observe that the kernel of dt is generated by T. Okay, and we just can consider H naught of E. This is W in H naught of L. This is of dimension R1 plus R2 plus 1, right? Because we have just R1 plus R2 plus 2, and we divide by CK, so the dimension will drop by 1. And by the previous discussion, we just get a class in K, and the difference here was 2. So we have to subtract 2 from here, so we get a class in K R1 plus R2 minus 1, 1 of XL. And now with some extra work, one can prove that this is non-zero. That's what they do. For curves, it's actually way easier to prove that it's non-zero. But it's non-zero in general. So this is non-zero. So the actual problem of deciding whether or not this class is zero, it's not that easy. But for this particular case, it's been done by. Okay, so I think I'll stop here for today and continue tomorrow.
Thank you, Christian.